In this video, we'll introduce a new type of neural network for unsupervised learning, known as the autoencoder. So in the previous videos, we've talked about the restricted Boltzmann machine. We said that it's a neural network for unsupervised learning. That is learning in the case where inputs only take the form of an input vector. So we don't have an associated target, or we don't use it throughout learning. So we're only trying to learn on the basis of only the input vector x. So this can be useful either to extract some meaningful features or to leverage somehow some large amount of unlabeled data that we might have in order perhaps to improve our performance on some particular task for which we have a little amount of labeled data. And we'll also talk, when we talk about deep learning, how we can use unsupervised learning as a data-dependent regularizer for training. And now in the following videos, what we'll consider is another type of unsupervised neural network known as the autoencoder. So the autoencoder is actually a very simple type of neural network. It's feed-forward, much like the neural network we've seen for classification. And the main difference is that it's going to be trained not to produce a class at the output, so not to define a distribution over a class at the output, but instead to reproduce the input that was fed to the neural network. So essentially, it's going to be, say we look at an autoencoder with a single hidden layer. Its output layer, which I'm now calling x hat, is going to be of the same size as the input layer. And when we're going to train it, we're somehow going to compare the values at the output produced by the neural network, the autoencoder, with the values at the input. And we're going to encourage the neural net to reproduce as perfectly as possible at the output layer the value that was fed in the input. And otherwise, this is just a regular neural network. In the terminology of autoencoders, will refer to the part of the model that computes the hidden layer, that computes h of x, as the encoder. So it's going to encode our input into a latent representation. And one form it could take, which is very popular, people usually use, is just the sigmoid of a linear transformation, much like in a regular neural network. And then we're going to have a decoder, which is going to take the latent representation h of x, the output of the encoder, and it's going to again linear transform it and pass it through nonlinearity. So if we have inputs that are binary between 0 and 1, then we use a sigmoid nonlinearity to squash everything at the output between 0 and 1, so it has the same range as the values we can have at the input. If we had other types of inputs, so if we have real value data, then we'd use something else. But so this output, which we're now going to note x hat, is going to be the decoded input based on the representation, the latent representation extracted by the autoencoder. Another frequent practice is to actually tie the weights between W and what I'm calling W star, which is the weights between the hidden layer and the reconstruction output layer. So by tying, I mean that W star would be set as the transpose of the connections that go into the hidden layer. So in other words, the connections going into the hidden layers are going to be the same as the connections that go out of the hidden layer. And one motivation for doing this is that this starts looking a bit more like a restricted Boltzmann machine. So like in a restricted Boltzmann machine, where we're going from the hidden layer to a space which corresponds to the same space as the input space, then we're usually multiplying by the transpose. And so in this sense, each hidden unit here extracts a particular feature, and then when we're trying to reconstruct, we're just putting back that feature into the input. Okay, so often we'll use that, but that's not necessary. If you see in a paper that tied weights were used, that's what it means, that the transpose connections were the same as this input. So when we'll do gradient descent, for instance, the gradient on W will, there will be a gradient coming from the hidden layer, and a gradient that goes directly through W transpose that will, of course, have an impact on what W should be. All right, so that's the main definition of an autoencoder. It's pretty simple, feed-forward neural network that is trained to reproduce its input at the output. And one motivation for training a neural net like this is that essentially we're training it such that the hidden representation maintains all the information about the input. And for instance, if we use a hidden layer that's much smaller than the input layer, then this means that the autoencoder is sort of going to compress the information. So ignore part of the input that is not useful for reconstructing it, and just focus on what makes the input special and what is important to extract from it if we were to be able to reconstruct it afterwards. Okay, so you could think that an autoencoder like this could be used for instance, compressing the data. But we'll talk about more how we can use it to extract some meaningful features for some given problem.